Hello, everyone. Welcome back to The Good Stuff. The Good Stuff being the AAS Author Series, where we take a AAS article and we walk through it with one of the authors. And I am super glad to have Kiran Eiden with us today. Hey, Kiran.
Hello.
How you doing?
I'm all right. How are you?
Good. Where are you at?
I'm in State College, Pennsylvania at the moment.
Oh, okay. I believe you're a grad student at Stony Brook, though, yeah?
Actually, I'm an undergrad, or I was an undergrad at Stony Brook. I just graduated this week. I'll be heading
congratulations to you.
Thank you. I'll be heading to UC Berkeley for grad school.
Awesome. Very good. Very good. All right. So I think you have the, you win the prize then for being the first undergrad to grad to do an author chat here. So that's just great. And hopefully you'll move to Berkeley soon, I guess.
Yeah.
Get through pandemic here.
Yeah, I haven't heard anything about whether classes will be online or not. I know the Cal State system is online for the fall, but
yeah, that's what I heard.
Yeah, we'll see what happens with that.
Yeah, we will see. One way or another, you'll start this August. So congratulations on that.
Thank you.
What do you like to do for research so far?
I focus mostly on type 1 X-ray bursts, and basically studying the dynamics of the explosion.
Cool.
X-ray bursts. So.
Very cool. And in fact, that will lead us into the article that we're going to cover today. So we are going to cover dynamics of laterally propagating flames in X-ray burst 1. Burning front structure. And Kiran, take us away.
Okay. So an X-ray burst is basically a big explosion on the surface of a neutron star that secreted material from a binary companion.
Okay.
So the material accretes onto the surface and collects to form a thin ocean of hydrogen and helium fuel, typically. And the gravity of the neutron star compresses that to high temperatures and densities, and that ignites a thermonuclear runaway on the surface.
Is that layer uniform across the whole neutron star, or does it like pile up at the equator?
It tends, I think there's some magnetic channeling that tends to funnel it towards poles, and
okay.
it's not entirely uniform across the surface. But that actually kind of leads me into the subject of this paper. A lot of what we know about X-ray bursts comes from 1D models that assume spherical symmetry, that assume it is uniform across the surface. And those models are great for studying nuclear synthesis and trying to predict things like the rise times of the burst, which is that the time it takes for the X-ray luminosity to spike during the explosion.
Okay.
And the recurrence times, so the time between bursts, because you can often get multiple bursts typically you get multiple bursts from the same source, and those occur periodically. But they've actually found oscillations in the rise of the bursts.
Okay.
And those oscillations are thought to be evidence for actually asymmetrical burning on the surface. If you imagine that the ocean ignites at a localized hotspot where maybe more fluid has piled up and you get a higher base density and temperature.
Okay.
Instead of the entire ocean igniting at once. It produces a brightness asymmetry on the surface, and as the star rotates, similar to the mechanism that gives us pulsars, you'd get oscillations in the luminosity as the bright spot comes in and out of view. So that's actually thought to be evidence for that localized ignition. And once the fluid layer ignites at that local hotspot, it kind of generates a burning front that propagates across the surface of the star. And in this paper, we're kind of studying the dynamics of that laterally propagating flame front. and specifically looking at the structure and what effect things like rotation have on the propagation speed.
Uh-huh.
So I think actually you can see it here. There's a lot in the intro, but I'd like to focus on two particular studies.
Sure.
First of them was by Anatoly Spitkovsky and company. I think that's up in the second column near the top. Yeah.
Yep.
So they were some of the about 20 years ago. They did a multidimensional simulation of localized ignition on the surface of the star. And in particular, they looked at how the rotation of the neutron star can affect the dynamics, and actually helps to confine that burning front to a sort of thermonuclear vortex on the surface of the star. It's the same mechanism that produces hurricanes on Earth.
Okay.
And they found that basically the Coriolis force can help confine it and reduce the propagation rate, and that's important in the dynamics. And they also found that basically hurricanes on Earth are kind of at a geostrophic balance with the environment, meaning that the pressure gradient is balanced right at the edge of the hurricane, and you get a tight vortex. Here, the vortices, the pressure gradients don't perfectly balance, and you get more of an expanding vortex.
Okay.
So it's this. So the size evolves as time passes, and that's kind of how that ageostrophic balance is kind of how the flame propagates.
Okay.
The thing with Spitkovsky et al. Simulations is that they use the shallow water equations, and they kind of did like a global study of what happens on the surface, but they couldn't resolve any details of the vertical structure of the atmosphere.
Mm-hmm.
So the first vertically resolved simulations in multiple dimensions were obtained by Yuri Kvecki et al. And Yuri's actually a co-author on this paper.
Yes. And
he's done a series of papers on this. The first was in 2013. So the geometry of this problem is kind of weird. You can kind of imagine zooming into at least for this first simulation, zooming into the pole of the neutron star and taking a cross section. So you'd get part of the fuel layer on top of the star, and then a little bit of the underlying neutron star. It's like taking a slice through it. And you can account for rotation by including Coriolis force and a third term. Third velocity component that's coming out of the plane of the simulation.
I'm with you.
And they basically set up a perturbation near the axis, like you can imagine like the left axis of the domain, and the flame ignites there and propagates from left to right across the domain.
Okay.
In that simulation plane, and they can study, and that gives them some insight into the dynamics while allowing them to capture like the vertical structure of the atmosphere. So Yuri has done a series of papers on this. First, they kind of investigated the Coriolis force and found that the flame speed is more or less proportional to the Rossby length, or that basically means it's inversely proportional to the rotation rate. The faster you rotate, the slower the flame propagates.
Uh-huh.
And he's also looked at the effects of magnetic fields, and recently, this last year, released a paper where they studied the effects in 3D, and in particular studied baroclinic instability at the flame front, which I'll talk about a bit more later. So for our simulations, they're very similar to Yuri's, but in basically multi-dimensional simulations of X-ray bursts are extremely expensive, and you really need to do some sort of approximation to capture what you want to capture. So in his case, they enforced vertical hydrostatic equilibrium,
All right.
which basically allowed them to filter out vertically propagating sound waves and increase their time step and use a larger grid.
Yep.
They also only use the triple alpha reaction for their implementation of nuclear burning. So we don't enforce vertical hydrostatic equilibrium, and we don't, and we use a more complete reaction network.
Cool.
But that comes at the expense of a few other approximations, which I'll talk about. So let's head to the numerical methods section. Yeah, numerical approach. Mostly what I wanted to say here is that we use the Castro hydrodynamics code, and that's built on this AMRX framework developed at Lawrence Berkeley National Lab. But it's a compressible hydrated dynamics code, solves the reacting Euler equations. So it's basically second order in both time and space. The other thing I wanted to mention is that we work in an axis symmetric cylindrical geometry.
Okay.
So if you imagine that simulation plane, that left-hand axis is basically a vertical axis. And then the radial direction is the other dimension that points along a longitude line. And
Kind of like a pillbox.
yeah.
Mm-hmm.
Yep, and then we assume it's symmetric about that vertical axis. So if you could take our simulations and rotate around that axis to turn it to a 3D simulation, which we're actually planning on trying.
Very good.
Yep. So although it's a 2D simulation, we have that third velocity component, allowing stuff to flow in and out of the simulation plane. And we actually neglect the centrifugal force here because we're not expecting it to affect the dynamics very much based on past studies, but we include the Coriolis force so we can sort of capture the formation of that vortex discussed in Spekovsky's paper.
Uh-huh.
Yep. And if you want to go to figure 1.
Figure 1.
Yep. So this is kind of a section of the domain. The black region at the bottom is the underlying neutron star. And then above that, we have the base of the fuel layer. This is a plot of temperature. You can see it peaks. Peaks maybe maybe right around 0.3 times 10 to the 4 centimeters there.
A few times to the 9th K.
Yep. Yeah, at about a gigakelvin.
Mm-hmm.
And that's the region where the burning is most intense. So that's the one we place at the highest resolution. What's nice about the AMRX framework is that it allows us to use adaptive mesh refinement, basically refining certain parts of the domain more than other sections. And that lets us capture, basically, one of the things that makes these simulations so expensive is that we actually need a 10-centimeter resolution around there
Okay.
to properly capture all of the nuclear reactions. But we can't, since the horizontal extent of the domain is actually on the order of a kilometer.
Yep.
We can't really place the entire domain at that, or at least we don't want to place the entire domain at 10 centimeters.
Sure.
So higher up in the atmosphere where there's not as much going on, we use a much coarser grid. And AMRX manages that for us.
Okay.
So that's really all I.
So this figure is at some point in the evolution of the laterally propagating flame. Yes.
Yeah, it's further along in the evolution. It was mostly to show the grid resolution. You can see the highest resolution is the blue grid near the center, and then as you go up in the atmosphere, it gets coarser.
Sure. And what is the initial conditions for this?
There we also have an initial model section a little later.
Okay.
That I can go into. Yep.
Okay. Let's slide down. And
yeah, before we do that, I'd like to discuss the flame properties section because that outlines one of the approximations we make.
Sure.
So the main issues with trying to simulate multidimensional bursts are just that they're incredibly expensive. And the length scales and time scales at play are much larger than the grid size and time step we need to take. So ideally, we would like to decrease the amount of time we need to see significant development of the flame and to see it travel across the domain by some reasonable amount where we can actually study the dynamics.
Yep.
So to do that, you can actually play a game of sorts. If you go up to the top of the second column, we have a few equations there.
Oh, there we go.
Yep.
Yes.
So for a laminar flame, just in the plane, with no. Basically, this is just a single layer flame, which you can study in 1D or 2D. We know that the speed of the flame goes like the square root of the conductivity times the nuclear energy generation rate, but the width of the flame, which sort of gives you the structure, of course, it is actually proportional to the ratio of the two. So we can keep the width the same and hopefully the structure the same if we boost both the conductivity and the nuclear energy generation rate by the same factor.
Okay.
But that will boost the flame speed by that factor. For example, if you boost both by a factor of 10, then the flame will travel 10 times faster, but you'd still have the same flame width.
Yes.
So in this paper, we consider only boosted flames because those will develop much more quickly and it takes less simulation time to run out far enough to see significant development.
So you mentioned that you're using a more complete reaction network, and of that reaction network, presumably you get epsilon dot here, the nuclear energy generation rate. So then do you take that nuclear energy generation rate and multiply it by whatever scale factor you...
Yeah, we do.
Okay, got it. I'm with you.
Yep. Also, something I neglected to mention earlier, for this set of simulations, we assume a pure helium composition. You can actually get something close to a pure helium composition if if the material it collects, it burns from hydrogen to helium as it accretes.
Mm-hmm.
That does happen in some systems, but vast majority are a mix of hydrogen and helium, but that's something we're hoping to look into in a future study.
Okay. Yeah, this is paper 1, so presumably there's a paper 2.
Yeah, we're hoping to get like 4 or 5 more at least out of this, but we'll see.
Okay.
Yep. And basically to test this boosting, we did a pair of 1D simulations. If you scroll to figure 2, I think it's on the next page.
Indeed.
Yeah, so we basically did a pair of simulations in 1D. So that means no vertical structure, just in the radial direction.
Mm-hmm.
And measured the position of flame as a function of time along with the flame speed. So the top left is the temperature profile, and beneath it you see the nuclear energy generation profile.
Mm-hmm.
And in the x-axis there is the displacement from the that left-hand vertical axis in our multi-D simulations. And you can see after there is a big jump from the first and second profile, but after that it propagates pretty steadily.
Yeah, there's the initial transient from the initial conditions.
Yep. And then and the flame speed and flame width both stabilize after a while.
Yes, they do. Kai-bai. Yep.
And in the table below that, we get the flame speeds. And for that 10-10 boost run, which means boosting both thermal conductivity and nuclear energy generation by a factor of 10,
Yes.
we got a flame speed around 1 kilometer per second. And then when we boost both by a factor of 5, we get about half that, more or less. So that seemed to indicate that this might work.
Mm-hmm. Cool.
Yeah, one thing to note here is that we'd expect the flame to speed up in multi-D because there are some multidimensional hydrodynamical effects like turbulence, wrinkling, convection that can help mix things up and help the flame propagate.
Yep, I'm with you.
Yeah, so that's all for that section. It's just to study the effects of the boosting. The next section is the initial model. So this plot's a little bit confusing if you don't have the background. Basically, our initial setup, we start with 2 models. We call them the cool and the hot initial models. The hotter one is closer to the vertical axis. That's sort of a temperature perturbation near the left-hand side of the domain. And then we have cooler fuel out to the right. So we actually start with two separate initial models that we blend at an interface. So it's somewhat of an artificial setup, but when we actually start the simulations, we see that relax into a more physical, something that looks more physical and the flame ignites properly.
Okay.
Yeah, and each of these models have 2 different scale heights, and each of them starts in vertical hydrostatic equilibrium. We relax that constraint once the simulation starts. But, so basically, we take the 2 models, blend them, like using a linear ramp at the interface.
Okay.
Yeah, so that figure shows the initial profiles. You see it's constant around 2,000 centimeters is where the underlying neutron star transitions to the fuel layer.
Yeah. Okay.
Yeah, so you see the temperature is pretty much constant down there. And then there's a brief ramp up to the peak temperature.
Uh-huh.
And then it kind of decays. And so we basically set up the initial temperature model, and then solve for the density enforcing hydrostatic equilibrium, which gives us the blue profiles.
Mm-hmm.
And the base density is somewhere around 3 times 10 to the 6 grams per centimeter cubed, and the peak temperature of the hot model is around a gigakelvin, and it's a little bit over 200 million, somewhere around 200 megakelvin.
Just above ignition temperature for helium burning, yes?
Yeah, for the cooler one. So I can go into some of the equations for the initial model, but I don't think it's really important here. It's important for replicating it, but
sure,
not really relevant to the results.
And here we go.
Yep.
Okay. So what have we here?
Okay, so there's one more thing I think we mentioned in this section. If you want to scroll down on this page a little bit, I think it shows it. Yeah. So you see in the bottom left corner the formula for the Rossby length. That's sort of that's basically the length scale over which gravitational and buoyant forces balance rotational ones. So that's kind of a measure of the horizontal length scale of the vortex.
Mm-hmm.
And it's inversely proportional to the rotation rate.
Yes.
So the other thing we do, our other main approximation, I should say, is to accelerate the rotation rate of the neutron star. For most of our runs, we use a rotation rate of 2,000 hertz.
Okay.
Which is probably 3 to 4 times what you'd expect to see for an X-ray burster. And that basically tightens the vortex, shrinks the horizontal length scale, so we don't need as wide a simulation domain. But we study the effects of both the boosting I discussed earlier and the accelerating the rotation rate by running a full set of simulations, not just one. So this table gives the simulation parameters. Basically, for the standard run, the one we use to study most dynamics, we called it the 10-10 run. That just means we boost by a factor of 10.
Uh-huh.
And we use a resolution of 10 centimeters at the finest level, so mentioned earlier, and rotation rate of 2,000 hertz.
Yes.
We also try to run with a 5-5 boost, factor of 5 boost, and one with a smaller reaction network, 7 isotopes instead of 13, 13 isotope alpha chain one. We tested it at lower resolution, and the last one, the 1,000 hertz run, was at a lower rotation rate. So we'll look at all of those in this section. The figure up at the top is from our main 10-10 simulation, and that actually shows the mean molecular weight in our simulation domain as at 5 different times. So initially, this blue purplish layer at the bottom is the underlying neutron star. That's we made that pure nickel 56.
Okay.
And then above it is the helium fuel. So that's the lower part of it. Yep. Yeah, and this A bar is basically mean molecular weight. So as the fuel burns, we expect to see that increasing. So at about 5 milliseconds, you can see we're starting to develop a clearly defined flame front, and you can see it's definitely burning to heavier and heavier elements. By 10 milliseconds, you can see it's starting to advance across the domain, and even more so at the later times. And the flame's much more developed, much heavier ash. Some two things to note are that the flame front's actually slightly inclined. You can see it's lifted off the surface of the neutron star. There's that yellow band of yellow running across the bottom, and that actually increases the surface area and can help the flame propagate.
Why doesn't that material burn?
We think it's partly due to convection and turbulence near the flame front. That tends to bring cooler fuel underneath and up into the hotter part of the flame. Well, the heavier ash is, you can imagine like a cyclic motion. It brings cool fluid underneath and heavier ash at the top. And a lot of that ash, you can also see a stream of ash here.
Yeah,
it's carried along ahead of the flame. It's kind of carried along the surface by, we think, surface gravity waves. These are kind of like gravitational oscillation modes.
Right. So they must be much faster than the flame speed in order to propagate it out front, right?
Yep.
Okay.
Yeah.
Okay. Very cool.
Yep. So that's the main thing to take away there. We also looked at a few other variables.
Okay.
I think the next figure shows that.
All right.
So this is the same simulation, but it's temperature at the top, then nuclear energy generation. And at the bottom, that's the out-of-plane velocity.
Okay.
So temperature also shows the flame front pretty clearly. You can see there's kind of, right at near the top of the neutron star layer, there's a weird transition here. Sort of rectangular cutout at higher temperature. We think that's a product of the initial model because there's a jump in refinement right at that location.
Okay.
So we basically initialize it on the finer grid and then interpolate to the coarser grids to fill the coarser grid data. And basically that means that the finer grid and the coarser grid are slightly out of sync. There's a small error there. We see this feature vanishes when we drop the peak resolution. So the neutron star and the base of the fuel layer are at the same resolution. So we think that's just an artifact of that initialization.
Okay.
The important thing in the enuc or nuclear energy generation plot here is that it peaks somewhere near the center of the flame at the base of the fuel layer. And we see that, so there's kind of, in the temperature plot, you can see that right where that black region ends, that's kind of the leading edge of the burning front. That's where stuff's just starting to ignite.
Oh, okay.
And the peak of the burning is actually somewhat back from that. Near where in that yellow region of the nuclear energy generation plot.
Right. So some combination of conductive transport and turbulence is the leading edge of the flame, and then the nuclear burning takes place behind that.
Yeah. Yuri Kavecki's group, we didn't really look at conduction in ours, but he found that through that sort of inclined flame front, you get like top to bottom heat conduction, which helps ignite the fuel underneath and carry the flame up along.
Cool, I'm with you. Yep.
Yep. And although we can't, since we don't have, working in cylindrical coordinates, since we don't have that azimuthal coordinate, we can't really look at the structure of the vortex, but we can look at the effect of the Coriolis force on the out-of-plane velocity. So the third plot here shows the gradient in out-of-plane velocity, or blue. We have blue back here. I think that's going into the page and then coming out of the page up here. And that gradient is set up by the Coriolis force, and it's sort of evidence for that vortical structure forming on the surface. Note that this is all in a rotating reference frame. So this white band here, it's the 0 point in that reference frame.
Okay.
So its absolute velocity is actually still, it's carried along with the rotation of the star.
Right, I'm with you. Okay.
Okay. And that's all for that simulation. Figure 6 shows the lower resolution run, and it looks more or less the same as the high resolution run, which means hopefully means that we're resolving everything properly. We do see more leakage in temperature. You can see in the top plot, there's that yellowish white region near the top of the neutron star layer, where it's not perfectly in equilibrium. And we see more instabilities develop at the top of the flame. You can see that in the A-bar plot.
Right, get these little characteristic mushroom type things.
Yeah, it looks like a mushroom field. But for the most part, it's very similar to the high-res run. So we hope that means that we're resolving everything properly.
We're more resolved in the 1010. Yep.
Yep. Yeah, and this one's for the 5 times boosted run.
This is 5.5.
Yep.
Yeah.
So this is also at 20 milliseconds, and you can see that's a lot less developed than the 10 times boosted run was, especially in the A-bar plot. But it's still qualitatively and structurally, it's pretty much identical. It just hasn't moved as far along.
Right, which you would expect given the decrease in the scale factors.
Yep. So that's kind of what we were going for. We wanted to preserve the structure of the flame and, well, basically hastening its development. So we didn't have to run out as far to see things start to happen.
Okay.
Yep. And for this is just a comparison. Figure 8 there is just a comparison of the 2 reaction networks.
All right.
We're hoping to use the smaller reaction network when we start our 3D runs, because those are really intensive. So we kind of just tested it out here. It looks pretty similar to larger network. The burning's less energetic, and it hasn't advanced quite as far. But for the most part, the structure is preserved. So that one might be an option, at least initially, when we move to 3D. And then the last one there is the run at 1000 hertz, which is half the rotation rate of our other runs.
Okay.
Yep. And you can see we enlarged the domain as well to accommodate a larger Rossby length. But you can see that the flames smeared out a bit more. It's extended more horizontally, but the structure is, again, very similar.
Yes.
Actually, we're finding that accelerating the rotation rate also helps the flame ignite, maybe because it keeps that perturbation near the left side of the domain, closer to the axis. And, so when we actually moved down to around 500 hertz, we found it was harder to get a flame going. And so the flame doesn't ignite as quickly as it does at faster rotation rates.
Yes. Cool.
Yep.
All right.
So we went ahead and measured the flame speed. The way we measure the flame speed is using the nuclear energy generation rate.
Okay.
When we first tried it, we just used the location where the nuclear energy generation peaks and tried to track that across all of our snapshots, basically, of our simulation. But we found that was oscillating pretty wildly. So instead, we picked a contour that turned out to be like 1/1000th the peak energy generation. That corresponds more or less to that leading edge of the right. Yep. And that was a lot more stable. And you can see in figure 10 there that that's basically position versus time for the flame front. And we actually get pretty linear propagation after that initial transient period where the flame relaxes and then ignites. So the blue, there are three lines that are kind of right on top of each other there. There's a green line corresponding to our standard 10 times boosted run. And
so the flame speeds here of order
a kilometer per second.
Right. Okay.
Yep. And basically the low resolution run and their standard run are right on top of each other. And then this orange line is the 5 times boost run. That's about going at about half the rate as the other ones. And then interestingly, when we have the rotation right, we get about double the flame speed. So the flame speeds, as Yuri Kvecki's group found, is more or less proportional to the Rossby length.
Yep.
If you scroll down to the table there, it gives the actual numbers in kilometers per second.
Oh, there we go.
Yeah, but they're all roughly quarter a kilometer per second.
10. Yeah.
Yep. And then the last thing I want to talk about was the baroclinicity.
Okay.
Somewhere before this, we give the formula for baroclinicity. It's basically a measurement of the misalignment of the pressure and density gradients.
Okay.
And in regions where you have high baroclinicity, you get high vorticity, lots of rotational fluid motions. And that, if you have a high baroclinicity at a particular point, you tend to get a lot of those vortices forming, and that can sort of entrain material along the surface of the flame here, where you see the baroclinicity peaks. This is in figure 11.
Yes.
Yeah, so it kind of outlines the flame front. So we think that helps trap hot ash near the surface and helps it propagate. That's something that will be a little more interesting to look at in 3D. And Yuri Kvecki's and Anatoly Spakovsky did a 3D run examining that. So we're hoping to do the same.
Cool.
Yep. Yep. And I think one more thing, if we want to go into that, I'm not sure how we're doing on time.
A little long.
Would you like a little long? Would you like me to wrap up then?
Let's go ahead and discuss these, and then we can move it on.
Okay, sounds good. So yeah, the last few figures, the streamline plot just shows that we get a convective cycle developing there. You can see the loops near the center of the flame.
Ah, yes.
We wouldn't expect it to look quite so nice in 3D, where you get a larger contribution from small scale features. But it's clear that convection plays some role in mixing the hotter fluid with the cooler fuel. And then the phase plots are interesting, that you kind of get, it more or less shows that you get loops in.
Oh, okay.
Yeah, this is just, the one on the left is planar velocity, basically, on the X and Y axes, and it's colored by nuclear energy generation.
Mm-hmm.
And the one on the right shows density and radial velocity, and colored again by nuclear energy generation. Just kind of shows the correlation between those.
Right.
It looks kind of like a ball, and
Looks kind of like a little bit set on the left.
yeah. But on the right, you kind of see that the energy generation peaks at not quite at the peak density, but just below it. So those were kind of interesting to look at. Ellis Harpole made these. She's a postdoc with their group.
Yep, Allison and Alice. Mm-hmm. Very cool.
Yep.
Okay, so this is paper 1, and so where do we go from here? Given this nice piece of work, what are sort of the next steps? What do you anticipate paper 2 would be?
So the first thing we'd like to do, that we actually have done, and we're hoping to get a paper out soon on, is relax those approximations, use a more normal rotation rate, and get rid of the boosting. We've ported all of the code we need for the X-ray burst stuff, at least, to GPUs, and we're able to run those, run on Summit, and we can see close to an order of magnitude boost in efficiency there. So we can actually do a run without boosting now on GPUs.
Very nice.
And we'd also like to explore different latitudes. Here we assume the Coriolis force was constant across the simulation domain, but as the flame propagates, they'll actually see the Coriolis force change, because there's a factor of sine latitude.
This is getting a bigger domain, which you can afford because now it runs 10 times faster. Got it.
Yep. And then the other things, next step would probably be 3D, but just last week we tried starting a 3D run on Summit, and our data files are on the order of terabytes.
Mm-hmm. I believe that.
So yeah, these are massive simulations.
Yeah,
they're highly intensive.
Transferring them becomes an issue.
Yeah, so we might want to actually run out a 2D simulation to some point and rotate into 3D and just run for a few seconds and few milliseconds in 3D.
Okay.
To see how things develop. And after that, maybe mixed hydrogen and helium bursts, where the RP process becomes important. So for pure helium, it's really just alpha particle captures that we're focusing on. But when you add proton captures, the mix becomes a lot more complicated. And
protons in the environment.
Yep.
Cool.
And and then the last two things that are probably ways off are MHD, including magnetic fields, and then trying to do radiation transport to maybe get some spectra, at least, maybe light curves from this.
Cool. That would be very cool.
Yep. But that's some time off.
Cool. Well, the future sounds bright. Lots of work to do. So we won't be running out of this topic anytime soon. So that's great. Kiran, I want to thank you so much for your time and describing your nice article to us. And for those of you who would like to learn some more, you can contact Kiran via email, whether it's probably changing from Stony Brook to over to Berkeley, but those in the game will be able to find him. And then we'll be putting some information about Kiran and the article in the description down below. All right, so thank you everyone for listening in on this talk, and we will see you on the next one. Thank you, Kiran.
Thank you.
Bye-bye.